Yes? Yes. All right. So, architecture for scale. But first, about us. Who of you guys know anything about ad tech or monetization, digital advertising? Anybody? A lot of hands. Well, it's kind of simple, basically. You have a website, turns out that there are a lot of users, costs go through the roof, you want to pay for it, you cannot, you start monetizing, you start advertising, you want to get some ads on it, and basically one way to do it is to talk to different advertisers, but that's kind of tedious and turns out to be a terrible business and actually a business of itself, and you want to focus on your content. On the other side, you're an advertiser, a game developer, you want people to buy your games, so you're searching for somebody who could advertise it so you get more customers. And it's also a terrible business to find all those publishers that would advertise your game, so basically you would turn to somebody that is Adcash. And Adcash is a demand-side platform. That means that we are focusing on the ad and the advertiser, but we're also quite extensive in our publisher base. Publisher meaning the websites that advertise your content, your stuff. So basically, we're an ad tech company, yeah, in a nutshell. We're bleeding edge. Well, aren't we all? But yeah, we use a lot of interesting tech that that really isn't common or wasn't. We started using Redis when it was people answered to the question like what, like you guys did for the WebQL. So now it's standard. So we were bleeding edge and we hope to be so further on. And we're also very international. The company hosts around 20 different nationalities. So even Estonians talk in English between each other. It's kind of weird, but it's pretty cool. Anyway, this is us. We started in an apartment and ended up on the cover of one of the most prominent publishings, Adcash in Estonia. Very proud moment for us. Anyway, that much about our company, and now about me and Anthony. So I myself used to be a developer, so went through all the development phases: junior, meteor, senior, architecture, senior architecture, software architecture, system architecture, solution architecture. Then went to the dark side about 5 years ago. I didn't really think it's the dark side, the management, but apparently it is. And currently I'm occupying the VP of Engineering position here in Adcash. And Anthony, a couple of words.
Yeah, so for me, I started as a developer here in PHP. I'm graduated from like a school in France for system development mostly. And I've been working in infra for like 5 years or so. I'm the infra architect, it seems now here. But I basically built the thing with the CTO here from the floor. So I guess that's it for me. Yeah, I think that's it.
So thanks. This is us. The presentation will be done kind of in two phases. First one is going to be a bit of a helicopter view. That's going to come from me. And then we'll dive a bit deeper into some of the topics that that kind of helped us around along the way. And this is going to be carried by Anthony. So yeah, the questions, if you have any, hopefully the slides will be done in such a way that it'll provoke some discussion or at least some lively questions from you guys. So you're welcome to ask them right away. Okay? There we go. Service-oriented architecture. That's the big word today. Everybody's talking about services and microservices, and well, it's super fun and super great and fantastic. So yeah, why we think it's really fun is because of the bold stuff that's on this slide. The abstraction, reusability, statelessness, nicely collocated stuff, actually less collocated, right? Providing autonomy in development, maintainability, end-to-end responsibility when you're working on a service, etc., etc., etc. Well, we do believe in service-oriented architecture, but we kind of don't at the same time as well. And down the line I'll explain why. but there are certain truths in service-oriented architecture. Specifically, what's important for us is the abstraction part. So we'd like to have something that we talk with or interact with that is very abstract. It is stateless, so you don't care whether it dies or whether it's there. You just care that it kind of works and you can spawn something new. And it's reusable, right? So you can scale easy. The other thing is that it's supported by all the modern SDLC practices, so software development lifecycle. Today it's really built in. It's built around the service-oriented architecture. So all the methodologies, all the tools that you have, they're all made for this, which is great, but when you don't really believe in this, it's also a bit terrible. You know, you have to reinvent the wheel sometimes. It scales organizationally quite well, right? You need a new service, it kind of, some part of functionality grows into a new service, and you basically staff up and you make it a nice, autonomous, self-sustainable thing, and there you go, right? If you're a monolith, then it kind of like, okay, who deals with this? And you know, the project ended and we have a new bug, and who wants to work on this bug, and nobody knows what the hell this is, so everybody's kind of pushing it away. So monolith, this is what happens, but SOA kind of has it built in there. And the DevOps culture, you know, we have a one-man army, does everything, infra, development, glue code, boilerplate, everything, you know, you just do it. That's also great, but here's why we kind of are in a jam, right? Why it doesn't really work for us. So what do we face? Well, the first thing is legacy, and that's, you know, kind of turns to the ball of yarn that you have there in the corner. We grew out of a startup, and in the beginning of every startup, the idea is to ship as fast as possible so that you're faster than your competitors and, you know, you don't go into analysis paralysis. Well, what this means is that you accumulate massively some technical debt, and this is going to haunt you for the rest of your life as a company. Hopefully not as a person, but that also happens. So legacy, yeah, big word, big word. A lot of companies really try to figure out how do you chunk your software up so that it actually becomes a service-oriented software. Well, we're also facing that trouble. Second thing is scale. Well, we have this legacy platform, and we managed to actually scale it up to such a grand level that, you know, chunking it up really would impact our customers. So we got to be careful about that. So we cannot just go and say, okay guys, you guys deal with this thing, the really cool cache that we can plug everywhere, and then we're just going to start using it. No, it doesn't really work like this, because everything is kind of interconnected. So you have to be a bit smarter about how you chunk it up and how you make it into a more edible piece.
Yeah. Can you hold the mic on a bit bigger distance so it doesn't like echo?
Okay, so it does echo. All right. The third thing that we have is latency. So the interesting thing about AdTech is that every event that brings revenue brings it on a sub-penny level. That's a bit of a problem, because that means that in order to make a substantial amount of revenue, you have to have a lot of those events, right? And in order to have a lot of those events, obviously, when you're on a website and you want to read an article, you're probably not going to be waiting around there for a minute or so when an ad shows up, right? You probably, like, it needs to be there right away for it to be effective in any way, right? And the perfect thing is obviously if you have the right content, right? But so here's where the latency comes in. You have a huge amount of those events, and you have to serve them really quickly. Right now, Adcash is operating at about 650,000 events per second that we process. And within that, we move around 7 to 9 petabytes of data every month. And there's another number I'd like to drop is the 10% of IPv4 IPs that we churn through, that's of the entire world. We churn through that every day. So it's kind of a scale, right? And our prediction system and our ad engine has to provide an answer within 20 milliseconds for this to actually work. So now you're kind of thinking, okay, so the scale and the latency, and then we actually have to go in there with forks and knives and break it down into smaller systems. It's a bit scary. The third one is costs. With such a system, the problem is that, if you go so away, you basically start having cost centers. So you say, okay, this service, you guys manage your costs and you just tell us in the end of the month how much it's going to cost. Well, what Uber does is like, oh, hey, I don't know, site reliability calls and says, hey man, I saw that your service doesn't work. So I kind of threw in a couple of 100 machines there. I don't know, you might want to look at it, but not really hurry. For us, it doesn't work like that because of the sub-penny level revenue that we have. If you throw in 200 machines at a service, right, what you're going to start doing is you're going to start eating away your margin. So that's a no-go for us. We're constantly monitoring the optimization of the software so that it actually meets the requirements that we have between the bottom and the top line of the company, so the revenue and the profit, right? So the costs need to be as uniform as possible for us to actually monitor this, right? You cannot just say, oh wow guys, we just spawned 2,000 machines and we just found a month later out about the whole thing, so no profit today, sorry. That just doesn't work, So costs need to be as uniform as possible. And encapsulation in this case doesn't really work for us. I guess we're also a bit paranoid and trusting a service guy with cost. I don't know, that's me, I'm sorry. And finally, the interoperability complexity. If you have a lot of microservices, all of a sudden, at a larger scale, what you find is that the services by themselves work perfectly. But what doesn't work is all those services together. And then you're trying to figure out what the hell is happening. Where's the deadlock, or what's happening, where's the problem? Figuring this out is actually a huge issue, And with the scale, with the latency problems, with the ball of yarn right there in the corner, it's really difficult to actually go in there and say, okay guys, we're doing service-oriented architecture right now, really. No, that doesn't go like that. So what's our approach? Well, we say minimum service granularity. Minimum service granularity means services as big as possible, but as little as necessary. Does that make sense? The second one is maximum collocate. In order for us to actually stay within the latency boundaries that we need to operate in, we need to collocate. There's just no other way out of it. Every bit of service granularity that you add adds an overhead in networking, and you really start facing issues, really. Plus the complexity problem, oh my god. The third thing is keep it stateless, right? So what if a big chunk of your infrastructure drops? You have another one right there, boom. Okay, so it's collocated, it's nice and abstracted, it's very stateless, and it's not very granular, so it's pretty easy to kind of figure out where stuff starts to happen. And the final one is business-driven decoupling. And this is actually interesting within the next slides that I'll have when we're trying to monitor stuff. So some might say, this is on the verge of heresy. What are you talking about? Service-oriented architecture, microservices, this is what we need to do. Well, this is a ongoing debate between me and Anthony. Someday I wake up and I come at work and I say that, come on man, we just need to go microservices, really we need to. And then Anthony just defends it for a week, that we don't. And I go home on Friday, I'm like, okay, yeah, we don't, yeah. But then I read a few articles and I try again. Yeah, but eventually he's right, so yeah, he's the smarter guy here. It's kind of like love-hate relationship. So it is on the verge of heresy, yes. The truth is somewhere in between. Yeah, but we're still trying to find out. We have some ideas where to implement the service-oriented architecture in a bit more granular way, but, well, we'll see how it goes. It's basically like a bet thing. Anyway, what do we monitor, right? So the obvious thing is, okay, yeah, machine metrics, you have this number of threads, requests per second on core, some pile-up monitoring, things like that. That's very infrastructure, site reliability related, right? What we also monitor is something a bit more complex. So for example, we monitor the impressions, right? That's a bit of a more complex metric. It doesn't tell you really where things are going wrong, but it tells you that things are going wrong. So if you actually have some more specific infrastructure metrics, then the impression metric, the one that you see here, the third from the top, this one will actually tell you, hey man, you better look at your stuff. And the third part, we also monitor costs. This is something I said about the costs before, that they have to be as uniform as possible. So, I mean, we have a lot of different monitoring set up for costs, but this one is like the highest level. So we have the computing, the storage, and the bandwidth costs. And this is the fluctuation per day. So we have a lot of auto scaling, and we really need to understand, for example, what is happening here. You know, so we were on a lower level, and then all of a sudden, boom, something happened. So we thought that, you know, probably we threw in a couple of hundred machines, but it turns out that it was actually software that we released, and that wasn't really on the optimal level. So now we're talking to developers on how to make it a bit better. And this is a very complex metric, actually. It consists of a lot of different inputs in order for us to actually calculate this. And we wouldn't be able to do this on a company level if we didn't go with the maximum, or sorry, minimum granularity. So it's only then possible. And at such a scale, when you need to react as soon as possible, you really cannot go super granular on your services. So early 2013, we were there. Anthony's going to talk a bit more about this slide. But this kind of shows the monolith part in 2013. And then in the end of 2015, we actually broke it down by business areas. So we have some programmatic ad serving, then we have direct ad serving, so basically serving specific customers, not the networks, not the other networks. And then we also have the UI system. And what we think is that the UI system, which is not really latency driven, could be a great candidate for service-oriented architecture. So between today and 2015, we've gone a long way, but we're still facing the pole of yarn, and we're still continuing to break it down. So far, so good, no questions. So I guess I'll hand it over to Anthony. Let's do this first.
Sure. There we go. All right. So I will just talk a little bit about the history here. So Agu said it very well. We have a monolith. We add the monolith. At least in 2013 here, you can see like some sort of block that is supposedly processing pretty much everything. That's the status of the company that was at that moment handling 55 to 90 requests per second. So around 6 times less, a bit more than 6 times less what we had before. And this system was basically, well, handling both the UI, database, prediction, serving of ads, web requests, whatever you want. So this was obviously scaled very badly by just copying some machines everywhere. It was bare metal, everything, so nothing from the, let's say, nice and shiny stuff that we have from the cloud. 2015 is actually the migration to the cloud, and this is what triggered us to actually move to more service-oriented system, even though you cannot really call the status of 2015 really service-oriented. And as Agu said, most of our service-oriented would actually come from the UI, because the rest is way too latency-driven for now to go there. There is, like, obviously this is simplification. I mean, there is a couple of other service breakdown in 2015, notably the prediction is actually separated also by business area, couple of service, communication, and layer of communication. I will talk a little bit afterward about one of the layer of communication that we set up for the front ends here for the communication, the web request. I will explain a bit later what we did. But yeah, so that's a bit the history and what we are coming from. Nowadays, we are actually looking into moving to a service-oriented on some part of the system, mostly for the DevOps culture, for the benefit that gives to the dev teams. They will be able to work a lot better, more responsibility for them, and also end-to-end, well, responsibility, but also for them better. Like, it's more interesting to work on a service from the start, from your database to the client, instead of working on one piece of software in the middle that someone kind of manage the interoperability for you. So let's in the presentation, I will talk about two things. So one of them is the data at scale. I will just talk about what we actually went through and what actually was our findings, let's say, to actually scale an application with all the data problem and requirement that we had. And the next part will be mostly about interfacing our requests and what we actually did to make our bandwidth or request per second go from 100K to 600K over a year, not even over a year actually. So yeah, so here for the data at scale, let's say that from where we were coming in 2013, the usual database for web application, we were running on MySQL, one MySQL server, very big, handling every request. Obviously, this doesn't fit latency requirements. When you go higher, when you want milliseconds treatment, this was definitely not going well enough. And it was not scaling very well. And the second thing was the data. The data was relationship database, as little foreignly as possible, because the guy who was dealing with the database structure knew that this would impact the latency, but still it was still a big MySQL table of 500 gigabytes, for example. It was handling all the rules of our system. So obviously this doesn't scale at all, just not at all. So the findings that we have mostly comes from our usage in the cloud. When we started moving to the cloud, we noticed that, well, if you try to push your application and you say, okay, guys, we have a database that is MySQL. Whatever you do, you have to use MySQL. That's it. This is the only thing you have. Work with it. Well, that doesn't bring very good result. At the end, our application was not so efficient running with this type of database, which is kind of obvious, but you don't really think of it when you're working on the application, because what you're saying is that, yeah, well, changing the database is very complex and take a lot of work. Writing a couple of requests or apps on your thing running the MySQL should take less time. So just do it. Well, that's a bad idea. And the second thing was, well, don't force your application to use the data in the format that you have. So if you tell them, hey, okay, I can make you a couple of MySQL servers more, some read-only slaves, so you don't have so much latency problem, but you still use the database as I did it before, that's it, it will work. Well, the guys are never going to be able to scale their app anyway. It just doesn't work. After a while, your data format is actually what is slowing you down. So this is what I will be showing a bit after with a couple of, let's say, examples. So, second thing, quite important for us, don't overdo the services around your app. So doing some services, maybe to share some data, might make sense. If you want to reach 650,000 requests per second with very low cost and still do 20 to 50 milliseconds treatment per request, then it becomes difficult to handle this with tons of microservices or tons of services that you have to communicate to. This is something that we did not discuss before, but basically our main app, so what we are talking here, the thing that brought all those findings, our main app is basically a system that does aggregation of tons of data. What it does, it says, I get one web request coming from a user on a publisher page, on a website. From there, I need to know, does this match any campaign on our system, any advertiser image we want to print on our image. So we need to go through all what we have, whatever publisher, advertiser we have, check all of their image and say, okay, that matches, that doesn't match. Then once we have all those images, we need to send that to a prediction service that will say, okay, for this image that you can actually display, you will probably get that much money. Then we need to check if any of this image have been shown before. And then once all those checks are done, finally we can display the image and hopefully get a conversion and get money. So that's pretty much all the process, and all this needs to happen blazing fast, so we don't really have the time to spend in network connection, network sending of requests to distant services and stuff like that. So that was mostly our issue with this type of service. So that's why I say don't overdo the services around your app. If you can cache data locally on the machine, and if it's possible for you to do it stateless, so when a machine comes up, it gets the cache is updated automatically, whatever, then this is absolutely perfect, just do it. It's going to be a lot easier for you to manage later on. Obviously, this also means be careful on what, and we touch it afterward, on what data you do, because, well, obviously if you sync 500 gigabytes of data on every servers, most probably that's not going to work, or you're going to have to pay like an arm and a kidney for your infrastructure to run. So that's definitely not a good idea. And on the second one, I say like mostly don't make your app do the hard work. What I call hard work is actually exactly the same thing: communicating with a service, crafting a query to whatever language you want, opening network connection, all that stuff. Keep it as simple as possible. Open, I don't know, a queue connection that is only once, that you keep all the time, and just drop everything there. And leave the other apps that are less latency driven deal with whatever is necessary. So for example here, we talk about our most specific case is the metric and statistics. So coming back in 2013, every time there was an impression, the request would actually go to MySQL and increment a line. So this would take around 150 milliseconds just because you need to find a line in a MySQL table that is over 1 terabyte big. So it doesn't make any sense. Like no. So this is why we are saying like this was a big problem, and actually it's the problem for everything. An app cannot spend time, I don't know, dropping debug metrics or monitoring metrics to a database. No, you have to keep that away from the system. So this is kind of, let's say, the biggest finding that we have when we were trying to scale the data, or trying to make everything work, let's say. And yeah, so in terms of like presentation, what I was telling you, so this is like what we had at the start. So a copy of application and core database. Obviously, this you all know the problem. I'm sure you all face them. The core database, if this is not one of those clusterized database already, or if it's a MySQL, then good luck scaling it horizontally. Most likely you will be able to do it vertically, but that's gonna last a time. And well, it's a single point of failure that is very stupid. So obviously you don't do this. You want to move away. If you see that, move away. That's like a runaway. So that's really, really bad, especially if you are SRE or DevOps, because that's going to be on you to fix that at night when it goes away. Then that's what that's our first step. So when we came to the cloud, we started doing this. We did not know much actually on how to actually handle the scale. Like we were very new to the cloud, very new to this like very big request per second handling that we had. So well, we tried what everyone does, mirroring. So that was, let's say, it was a good idea at the time, at least the only idea that we had. It works okay. But at that moment, you will actually notice that the performance and, well, obviously, the read-only database has to be somewhat compatible with your core database, right? So most likely, it's going to be the same technology. So you're still imposing this limit to your app. And like aside of that, you're again imposing your database, your data schema to the app. So this is, well, obviously a lot better. You don't have single point of failure. You have some load balancing. You have vertical and horizontal scaling possible with the mirroring. But still, like thinking back of that, we should have thought of something very like simple, is that, well, you should process your data before this mirroring thing. And at the moment you do that, you actually decouple completely whatever is your read-only database, whatever is your database, and you also give the developer of the app the possibility of working with data that makes sense for them, like not having to do relationship over 10 databases, but maybe denormalize everything into one key in Redis. And then the guys can get all the data in 1 milliseconds or 2. So this was, let's say, this was an idea that we had in the middle. So obviously the trick here is on how you store the data. If you process the data to put everything into a text file, it doesn't really work out, obviously. But for us, this was like actually quite of a revelation, let's say. We were like, okay, why didn't we think about that before? But what we did is that we did some sort, like this processing data that you see here is actually some sort of inverted index. So kinda, I don't know if you know what is an inverted index. It's kinda like what you have in Elasticsearch. right? So when you do a search in Elasticsearch, obviously the thing doesn't go through every of the lines or every of the document and try to find in each of them which word is there, because otherwise it will take a year to get you the data. So what they do, they create an index that for each word, they have the list of document that matches. So basically we did exactly the same. We were thinking core database is still a MySQL database that does its job very well, no problem, but it doesn't do anything with the data at scale now anymore. And how we do that, we actually created denormalized data indexed, indexed by what the application has as value. So for example, the user or the website it's coming from, stuff like that. Right now the technology are separated. So before this mirroring thing was everything SQL. Now the fast read-only database is basically Redis. Everything is under Redis there. We did a little bit of trick there, the custom software, where we actually modified the code of Redis to have a couple of comments that are not available yet in Redis. They are not yet in open source, because to send it to Salvatore and making open source, we actually need to do a lot of work on cleaning it up. But basically what the system is doing is completely integrated in Redis, which for us is a very good point, because we actually end up collocating the Redis on each of the application server via simple replication, and makes the latency near to non-existent. So requests that were before taking around 200 milliseconds, between 100 to 200 milliseconds to get all the data needed to make a request, NAD request, right now takes under 8 milliseconds in best case. Yep.
But then you sacrifice consistency of the data due to, like, if
yes.
a visitor just been to one site and then
so
Redis doesn't know about it yet.
So yeah, so very good point. So here this diagram is obviously simplified to show only the thing, the data part. That's something I missed in the explanation. In the data, we actually talk mostly about it's not static data, but let's say data controlled by users. So for example, you're a publisher, an advertiser, go on our website and you register a website, right, or a campaign. You change the parameter of this campaign that should show on France or on Estonia or on Italy or something like that. So this is the parameter that goes through this process. What you're talking about is operational data, which is like, okay, this user has seen the website or not. And this we actually keep in clusterized data that is available on the system and like not collocated with the system. And I don't know if you know the technology, but we use Aerospike for that. Aerospike is basically like a key value store, clusterized key value store with extremely high access performance. It's very close by to Redis, even though it's clusterized. Very close by to a single Redis. So it's pretty good, and obviously this is something very important. You have also to know your data. So these operational data are separated, and they kind of act like a service. So you talk to the cluster as you would talk to a service, right? In just that the protocol is Aerospike. We make sure that this is separated because, as you said, that would break completely the consistency. But on our side, it would even not be just sacrificing some consistency. It would be throwing away the whole application. Because you cannot tell your client, I don't know, I show your ad 2 times per user, and then you end up showing it 25 times because of the consistency. It doesn't work either. So yeah, very good question.
So if we speak about Redis right now,
yep.
is storing that advertisers data.
Yeah, for example.
It's also store data about how much money he remains for campaign. So how?
Very good point. Nope, they are not stored there. They are also in Aerospike. So this is operational data. So for us, it's a very good point. It shows exactly something that I missed that I should have explained. It's extremely important to identify what is your operational data that should stay consistent as much as possible, and what actually can wait. And most of the time, like this is for us, this was our discovery. So that's why this was a revelation, actually, that we were sure that everything was very important to be very consistent, and always the guy click on the button, save his campaign, at the milliseconds the ad serving needs to know that it saved a campaign. Well, actually, no, you don't care. You can wait 5 minutes that the campaign goes live, that's fine. However, you're completely right. You cannot wait 5 minutes to withdraw the money from the wallet of the guy, because otherwise you're just going negative. So yeah, very good point. We actually do use it, well, we do separate it from this system to make sure that there is no risk of us like going bad, let's say. Sure, yeah.
So with regards to the operational data that Anthony's been, like the term that Anthony's been using, basically it's like in our system you would view this core database sort of like a disk in a computer, and the operational data sort of like a RAM thing. So yeah, we make a distinction between those two, and then so the RAM part, the operational data part, we try to you know, make as available as possible, and we cache the hell out of it. So yeah, so that it kind of complies with our latency constraints. But everything else, so we really went, you know, we had a deep dive there, and we figured out what part of the data is operational, what is not, and then we tried to make the non-operational data as smooth as possible to flow into the application for further on usage. So that's the kind of the distinction.
Yep, and also another point is that this operational data is usually very like small amount. You don't usually need a terabyte of those operational data. For example, as you said, the wallet, while it's stored on integer for us, all good. It goes very well. So you don't need much space there. So you can like handle it faster, much like RAM. So definitely. Yep. So like pretty much that's the, let's say, explanation from our journey from like a monstrosity of one MySQL ruling them all and making everyone lag to something that actually works out now. Yeah, so I did not have slide to explain how we built the inverted index. If you want, after the presentation, you can come and talk to me, and I can tell you what we did there or how we did it. But yeah, I basically skipped this slide. Yeah, so I will basically move to the next part, let's say. So now we were talking about data. So you have a good idea on what we did and how we try to work our latency through data. So now I will talk a bit about interfacing. So how we actually made the request comes to our infrastructure, which was not so easy. I will explain to you afterwards. So basically, we call it worker queue concept. Why? Because when we started here, we were, as usual, like everyone, we had a couple of Nginx servers, a couple of fast CGI server, and well, you have Nginx, you push request, you are happy, and you hope it works. Well, that scales well, but there is a lot of dependencies there. For example, something that is completely obvious. If you don't have service discovery, good luck doing autoscaling, because your web servers needs to know where the hell is your worker or fast CGI server in reverse way. So this is one thing that we decided not to do, collocate our web server on top of our worker server, because the workload is very different. The usage of CPU or RAM, for example, was very different, so tailoring a machine there would have cost like tons of money to actually make it correctly. So we decided to go with like trying to transform everything that we have into some worker queue. The reason for that, one of them was, like said a bit before, we tried to keep everything stateless. Because when we went to the cloud, first thing we did is deploy our whole infra and start activating autoscaling everywhere. And then we paid so much money that we did not have any budget anymore after 2 months. For the whole year. So we already said, like, we noticed that, well, you know, kind of dangerous thing to do, maybe need to be more careful. So so we actually discovered that Google has a very like cool thing, the same as I think Amazon is called Spot Instance, in Google Cloud it's called Preemptibles. You pay a lot less money for the same machine, but you have a possibility that someone bid higher or for the price on the machine, and Google will shut it down. So, you know, and you will have to wait for your machine to come back. When we discovered that, we actually decided to go, well, for this, because it's so nice and it costs less. And then we were like, oh, the only problem is that the machine leaves that minimum and that's the only guarantee you have, 90 seconds. So if your machine boots and dies straight away, you just had time to load your cache, and you handle a couple of requests, and then you have to start again. You need to kind of find a way to make sure that this machine can be kind of stateless as much as possible and load caches like fast enough so you could make use of those preemptives. So that was a very important point for us, trying to make everything stateless. Then goes the autoscaling, which goes kind of end-to-end with this. And the last and very important part for us is the reliability. So we had scaling, we had reliability and low amount of maintenance. Why we're talking about that is because right now, and that was not even the case 2 years before where we were 3 only, but right now we are 5. To handle all the traffic that goes through the company, the 1 to 2,000, 2,500 machines depending on the peaks and stuff like that, we are 5 people. And that's not so much actually. So we noticed that, well, maintenance is quite difficult for people. We don't have time to do anything if we have to spend it on maintenance. So this was one of our most biggest focus, let's say, and reason to do this. And yeah, the thing that we discussed before, obviously this doesn't work for every system. I would say if you have a classical website that have pages that loads for 5 seconds, maybe you can spend this time finding where the server, spend some time finding where your worker server is and send the query there. On our side, since we have milliseconds to wait, and even the web requests are short-lived in any case, it's better to go for something a bit more, let's say a bit more simple and flexible than doing this. So what we did, well, message queue, well, to bring easier scaling for us. Well, it's out of the box basically. You don't really need so much service discovery or configuration management with this system. I'll show you a bit afterward why. And you have the possibility to handle failover and traffic control very easily compared to if you are actually managing your configuration directly from the web server. Obviously, web servers have already inbound, handled system, or integrated system to handle this, but they are often not enough, especially if you are working in the cloud and not making use of, for example, Amazon direct load balancer to your servers and stuff like that. And well, the last thing and the most important one, the service discovery is not that mandatory with this system. What we did looks like this. So we are all web servers. Right now they are all running Nginx, actually OpenResty to be precise. And the balancers, which are actually not separated machine, they are integrated. We run HA proxy, which is I would say the reference on this if you want to run a simple software balancer. It's extremely powerful. The queues are all redises. Then again some HA proxy and the worker, which is running some obscure Facebook technology called HHVM. Yeah.
So this first balancer kind of works like a mediator. So
exactly.
Okay.
So it's exactly this, and that's where I was saying the service discovery becomes not that mandatory. Why? Because let's say your traffic is moving from, I would say for us it's from 400 requests per second to 650 during the peaks. So you know exactly how much one core Redis can handle. This is extremely easy to pre-plan. Because it's always the same thing. And all your traffic moves, you can plan and do what we basically did. So these queues are static machines. They don't scale or stuff like that. And we have a lot of cold ones. They are ready to be booted. They can be booted automatically, everything you need. But then you don't need service discovery. You don't need to spend time on service discovery because the only point that requires configuration management is your queue. And most of the system for queue system right now, if you take Rabbitmq for example, can even do that in clustering, so you don't even care about this, and you can still scale it horizontally. In our case, we use Redis mostly because of the performance. We had some issues. Well, let's say not issues, but we did benchmark, and we actually see a big difference between those two. But yeah, so that pretty much looks like this. This thing is actually a custom software that we developed in Java that handles pulling the requests from Redis. And for Nginx or OpenResty, it's actually a Lua, little Lua part that pushes every web request to Redis. So what we do, Nginx doesn't care at all what's going on. It just takes a request, push it to Redis, and then wait for 8 seconds at maximum on a key in Redis that the response comes by. If it doesn't come by after 8 seconds, we consider the request dead, because anyway, like, to be honest, after 2 seconds it should already be dead. So this is completely safe, and this allows us to basically handle all our scaling, all our reliability. This worker are preemptible. They go away like every 5 minutes we lose a machine, and this still works. Yep.
Are your all workers spot instances, or do you like
Yep.
separate them like half of them? But if they are all spot instances, there is always a chance that in Google Cloud or Amazon, when you try to launch some spot instances, there is no instances anymore because they have also limited amount of instances.
Yep.
And if somebody uses all of them, you cannot launch it. So
Yeah, so it's very true. The business model of spot instances and the preemptibles in Google, we don't run Amazon, we run only Google, so the business model is a bit different. They always have reserved amount of data for preemptibles. The only difference is the amount of burst, let's say, buying, but you're completely right. There is a risk that someone buys out the whole zone in Google. It's possible. It's handled by having multiple zones handling the traffic. So we basically have like this model replicated in 5 zones or 4 zones actually in Google. And if this starts happening, if one zone drops down because we are losing machine, other zone will pick the load up, and those zones are physically separated in Google, so they are the resources are separated. So usually this is okay.
and question to this, how much extra latency does actually like failing over to different availability zone mean?
Well, depending on the processing, I would say that if something goes down, like if the zone, if you have a crisis scenario, like someone buys all the machine, then the switch can be up to, I would say, 15 to 20 seconds. It's very slow because it needs to boot new machine, right? But for us, actually, the important part is that the system in itself will not suffer completely from that. It's not great, but it's still better to lose a bit of traffic, which is what is going to happen for us. We will lose a very little amount of, like around 2, since it's 8 seconds, we will lose like around 2-3 seconds, of gathering of traffic, and then the rest will basically be handled by the failover.
I mean, like after you failed over successfully, forwarding requests to different availabilities on how much this extra latency is.
Yeah, so that's the magic of this thing. It doesn't do any latency. So why? Because the failover is actually done on this level. So when we have to failover, this is in, like, let's say static machines. So it's in one zone in US. We have the same in the other part of the US, and those workers actually work. Like they pull from both zones. Okay. So what happens is that, okay, this worker goes away, that's completely fine. The other guy is gonna pull from this all the jobs that are not there. So here it's like no latency, no loss. And the worst case scenario, which I was talking about, is if this whole availability side goes away. And in this case, the failover to the other zone is actually made on the top level. So on DNS level, you will lose the IP will start. Every request will start going to the other availability couple zone, and at that moment you will scale all the data up. Yep.
Why don't you, like, as a backup plan or just in case, make, let's say, 5% of these spot instances like on demand, so they are like always up and running, and like the rest of them on spots, and then you pretty much mitigate the risk of like the default zone going down. Exactly.
So we had that for a year and a half. We had actually 10% of our infra running normals and the rest running preemptibles. It's very simple. It's, I would say it's called risk management in this case. In a year and a half, we never seen preemptibles dropping more than 25% of the zone availability. So it's never necessary for us to actually keep it in normal. So that's the only reason. Otherwise, I completely agree with you. We actually have dead groups. So basically instance group that are set at 0. If there is some gigantic problem happening in Google and they actually drop this, we will start scaling those ones manually actually. So because we don't need them and the cost is actually 60% higher. So unless there is a justification, there is no need for them. Yep.
Yeah, so basically it's just it's a risk management question, right?
Yeah.
1.5 years keeping alive the normal machines or non-spot instances costs A, and the end of day scenario costs B. If A is more than B, then you go with the solution that we have. So yeah, simple.
Yeah. So that's simple, yes. There is obviously a couple of other consideration, but that's usually, let's say that's our experience. Yeah, our CFO is just looking at us. Yeah. So
It's not that simple. It's very difficult. Gave it a lot of thought.
So yeah. Yeah, basically, so that's basically it. The failover, like this is an important part actually, like looking at the failovers and the reliability. The reason is that we don't want this, the fact that the machine goes down, waking us up at night or stuff like that. So that's the reason why we looked so much into it. And I can tell you that we were very careful with that, because nobody wants to be waken up by a call saying there is no more machines in Google, so you have, I don't know, you know. Yeah, you serve the request yourself, you know. I don't know. So no, we are definitely not doing that. So yeah, so that's I would say that conclude the presentation about the like worker queue concept and what we did. So that's two of the things that we described. I think there is no real answer, like no truth on like how to make something at scale. If someone comes to you and say, here is the document, buy it from me, this is the book that will explain how to make your application scalable. No, that doesn't exist. You need really to tailor that to your own use case, and this is like basically the only answer. This slide is a bit of what we are actually expecting doing later on. One thing Agu already talked about is the service-oriented architecture. We actually do want to go there, mostly for our GUI, mostly for our website or backend, because this gives so much more flexibility. For our ad serving, we're definitely not there yet. We're not moving there at all for all the reason mentioned. Service discovery, yeah, configuration management. I would say that this is something that most of the people who are building something from scratch will think as the first thing. Do you need to have that around if you want to scale? Well, unfortunately, we are still dealing with legacy, so this is on our table. We really want to get it running for some of the system, and maybe end up making those queues auto-scaled also. That would be amazing if one day it happens. Geo-sharding, very important thing for us. We are talking about latency, failovers, traffic controls. Currently, we do everything in the US. Actually, this would be a very good point, like trying to actually have failovers continentally also to make something better. Latency, we are talking about like 20 milliseconds. Actually, our limit, our customer limit is 100 milliseconds around here. The reason why we need 20 milliseconds execution is because everything is in the US. So for the traffic for Europe, you actually need this 80 milliseconds mostly just for the network. So having geo-sharding would actually give us even more power. Well, DevOps and data as a service. DevOps, I think everyone wants to do this at one point. For us, our organization is not there yet. We are moving slowly into this and actually making it work. Trying to push the developer more responsibility on infra, understanding what means hardware, and designing your software aside with the scale, with like thinking on how to install it later on, how to scale it later on. And data as a service, well, that's a big thing on our side. We actually have a very complex data system, I would say, because this is our core business. If we don't keep statistics, if we don't keep metrics, well, we basically cannot bill anyone. So this is a very important part, and we are actually looking into making this more flexible, more service-oriented than it is currently. So yeah, that's pretty much our nice plan. So here we go. Thanks.
Wait.
And if you have, voilà.
Okay, guys, thank you very much. And if you have any questions,
Yes.
then we're kind of going around here. The other thing is that if anybody has done anything to auto-scale data, then we would be one giant ear to listen to. So
Yes.
yeah, that would be really interesting. Anyway, thanks a bunch.
I think you guys, we can still fit in maybe a couple questions. If
Oh
you don't
yeah,
mind.
we have time, no problem.
All right.
You want to think?
Or yeah.
Yeah.
Just about the data scaling. Right now, you're saying that you're pretty much manually or custom launching this. Where, Google is in cluster scaling, this MySQL and stuff. But
Yeah.
for example, if you are talking about like scaling data and costs, have you guys tried non-relational databases like DynamoDB or Google alternative? I don't remember
Yeah,
the name.
it's so basically the thing is we have, when Agu is talking about auto-scaling of data, we have two parts of the auto-scaling. One of them would be the SQL, which for us actually doesn't really matter much now because we transform the data and we scale it. We scale actually the transform part, which scale very easily in a key store, the key value store. Thank you. So basically, this is the thing. The other part of the data is mostly actually stuff like Hadoop based. We actually run Hadoop and Grid as a database, and this is the thing that we are eagerly looking for someone who would have a magical idea on how to autoscale, because this is extremely complicated, like to actually give all the benefits of those databases and still autoscale it. So you're right. One of the solutions would be to run Bigtable, which is the equivalent of DynamoDB for Google. Unfortunately, this costs a lot of money, really a lot of money. So you actually don't spend much on storage, but you spend on processing. And currently, we do exactly the reverse. We have to buy servers for storage, but the processing comes bundled with these servers. So it's, difficulty. Let's say this is the problem that we have. So we tried BigQuery, and we actually use BigQuery even for some workload, but we cannot replace our whole data lake with this, unfortunately, and this is something that we are looking for.
What about caches?
Yeah, of course. Yes, Agu was asking if we can auto-scale caches. Yes, we can, because we use them in Aerospike and Redis, which are like very easy to scale, so that's usually what we do. Any other question, guys?
Spike is something like Hazelcast and memory data grid.
Yeah, exactly. It's kind of close by to this. The advantage of Aerospike, I would say that the guys put a lot of thought on having this cluster, communicating over different location, geographically managing like the replica, much like something like Cassandra, but without all the overhead of dealing with a Cassandra, basically. So it's kind of like a Redis, but that works cross data center, geolocalized, and that does the replication and replica factor easily. Yep.
One more question. You were talking about the stateless and then using the spot instances and having latency of launching a new instance, which is usually 20 to 1 minute, 20 seconds to 1 minute.
Yep.
Are you guys planning to go serverless maybe to actually have scalability right there and not to worry about launching servers and stuff? So
this is a very much ongoing discussion. We are not yet sure on how it works, also because we have a lot of our processing is also quite complex on the workers, so going serverless means abiding by some rules that currently we cannot really match on our workload. So it's actually an ongoing discussion. This is something that we are, let's say, investigating. We're not sure if it's going to be the future for us or not, but definitely something that we're looking at.
The thing is that when you put the spot instance up, then you have a really low response time. But with serverless, you can have over 30 milliseconds every time. Every time you call the function.
Actually, it's called the cold boot, but it happens only once. But if you use a serverless, if you're planning to do like they do 600 requests per second, then it's actually going to scale to pretty much instant answer. So it's only going to happen on the first request, but if they have constant requests going on, that problem is not going to happen.
So it will keep it warm at will.
It's only going to happen if you haven't had requests for, let's say, a minute or something like that.
Yeah, but that's definitely something that we are looking at. It's just right now the solution for serverless actually don't fit any of the necessary thing that we have, but it's something that I would say that in a year, maybe two, they will have so much work around this serverless that most probably we will be switching to it. But let's see. I'm just doing the oracle right now. I don't know.
I don't know. It kind of sounds like a cloud agnostic solution. Everybody's talking about it, but where?
It's a bit. For now, it's early.
It's hard. It requires pretty much to rewrite your existing workers.
Yep.
Rewrite everything.
Well, thank you guys so much.
Thank you.
Let's have a